Hello, hope you're doing well here. So this is lesson 10.1.5. We are doing 10-52 and 53 since we didn't get to class today. And so 10-52, it really isn't much of a circle question as it is more of a cylinder question because it is a slice of a cylinder here. And so it has a 6-inch diameter and is 2 inches thick. After a party, only a sector remains that has a central angle of 45 degrees. So we're finding the volume of the cheese that remains. So remember, the volume for a cylinder is the area of the base, which is a circle, times the height. But we have to keep in mind that this is a fraction of a whole cylinder. It has a 6-inch diameter, which means that the radius is going to be 3, and the height would be 2 inches. So this is what we got so far. So here's what the normal volume would look like. Volume is equal to pi times the radius, 3, squared, times the height, which is 2. So we would have 3 squared, which is 9 pi, times 2, which is 18 pi. But that's the volume if this was the whole cylinder. Well, what about the sector, the 45-degree angle portion? So we need to multiply by 45 over 360. But this actually reduces into a smaller number here. 45 over 360 is the same thing as 1 over 8. So it's really 18 pi times 1 over 8. And remember, when it's usually just a fraction like this, we usually just end up dividing by 8. Now, while 18 doesn't cleanly divide by 8, they both cleanly divide by 2. And so we can just simplify this by saying this is 4, because 8 divided by 2 is 4. And then 18 divided by 2 is 9. So our answer as an exact answer is 9 pi over 4 inches cubed. If you were to plug this into your calculator, I'll show this here. It'd be 9 times pi divided by 4, and you would get 7.069 if you were to round there. Okay. 7.069. Okay, so this one's pretty straightforward here. Again, 10.1.5 is supposed to be meant as sort of a review slash sort of like preview for future chapters. All right, 10-53. Dennis plans to place a circular hot tub in the corner of his backyard so that it is tangent to a fence on 2 sides, as shown in the diagram it writes. Our first goal is to prove that AB is congruent to CB. Okay. Now, with this in mind, we have to first know, okay, well, what's going on in this picture? Well, we do know that we have tangents here, right? Going from BA to the circle D and BC to the circle D. So we have to think, okay, well, what can we start with here? So first, we know that, well, we can make some radii here. And so I can go straight from point D to point A. So I'll do that first. And from point D to point C. So we first know that AD is congruent to CD because all radii are congruent. Next, if we were to draw another segment going from D to B, because we want to split it into 2 different triangles, right? Then DB would be congruent to DB because of reflexive property. But what's the last thing? What's the last thing? Well, here's the thing. If we have tangents, we learned the other day that tangents are perpendicular to the radius of the circle. So we have 2 right angles here. And so because we know that DA is perpendicular to AB and DC is perpendicular to BC, so because we know this implies, and that's what this little arrow means, this implies that angle DAB is congruent to angle DCB because they are right angles. So based off of what I have so far, I'm going to write this in blue. Here are my markings. I know that my radii are congruent. I know that I have right angles. And I also have my reflexive side. But if you were to look at this, you weren't careful, you'd probably think, Mr. Chun, this doesn't work. This is side-side angle. This is the forbidden property that I specifically mentioned. Don't ever use in a problem. You are correct. However, remember, there is a condition called hypotenuse leg. And this actually holds true for both of these triangles, because DB actually acts as the hypotenuse, and AD and DC are legs, and we have right triangles. So these triangles are congruent. So ADB is congruent to triangle CDB because hypotenuse leg congruence. Okay. And so now that we know this, if we were to do this as a flowchart, we can now say AB is congruent to BC because of CPCTC. So that was sort of a mini proof right there. I know we haven't done these in a long time, since like the beginning of second semester. So that's how we would do that here. Now I'm going to erase this. Feel free to go back and rewind this video if you guys need to look over it again. But now we're going to go to part B. What we basically just proved is that if two tangents go from the same point into the same circle, then we know that these sides are congruent to the tangents are both congruent to each other. So here we go. The switch to turn on the air jets is located at point B. This is the switch. If the length of the diameter of the hot tub is 6 feet and AB is 4 feet, this is 4, how long does his arm need to be for him to reach the switch from the edge of the tub? So assume that Dennis will be in the tub when he turns the air jets on, and that the switch is level with the top edge of the hot tub. Okay. Well, we got to think about it in a different light here. So if I were to recreate that same triangle that we just did for part A, here's what it would be. Actually, I need to use the line tool here. Okay. So big detail here. The diameter is 6. What does that mean? The radius is 3. So this length right here is 3. This length right here is 3. And this length right here is 3. But I hope you see this here, because we have tangents. We actually have right triangles. And more importantly, not just any right triangle. It's a 3, 4, 5. So that means DB is equal to 5 units. Right? Or 5 feet, I should say. Now, why is that important? Well, if DB is 5, we know the radius going from D to the edge of the circle is 3, right? So how much more feet does he have to reach? Well, it's just 5 minus 3 feet, which is 2 feet. That is the answer to the question. So I hope you realize there's a lot of things that you can take away from 10-53. The first and foremost is that I want you to know that when you have tangents coming from the same endpoints, going to the same circle, these tangents are going to be congruent and they make right angles. That's the first important thing. The second important thing, trig will never stop in this year. Trig's going to keep coming up no matter what kind of questions we're working with. So be familiar with 3, 4, 5, right? Be familiar with 30, 60, 90. So be familiar with these things, okay? It's going to come up a lot more than you would ever realize. All right, the last thing that I want us to finish off with here, I know 10-50 was pretty crazy and whatnot, so I just want to make sure that I'm clear with at least vocab for this circumcenter. So feel free to write this down as notes. The circumcenter is the intersection point of the perpendicular bisectors of an inscribed triangle. Circumcenter is the intersection point of the perpendicular bisectors of an inscribed triangle. This is also the center of the created circle. Okay. Part C, when we did the medians, this is what we call the center of mass, or the centroid. Specifically, this is the intersection point of all of the medians of an inscribed triangle. We're not going to really see this one in this chapter, probably in a future chapter. I believe it's chapter 11. So we don't have to worry about that right now. But that will be helpful to know in the future. And I think specifically in chapter 11, there was an activity that we would do where I would have you cut out a triangle and you'd have to find the center of mass. And when you cut it out and you put a pencil on that point, as long as no one's like breathing on it or there's no wind or whatever, it should stick up theoretically. So everything has some sort of center of mass, as long as some sort of object with a mass. And so just to give you guys an idea here, but hopefully this helps. If you have any questions, let me know, but appreciate everyone tuning in.